Okay, so let's continue our discussion on unitary and orthogonal operators. So we were discussing about unitary and orthogonal operators, right? And the last thing which we did was we set a number of equivalent statements in order to characterize the unitary and orthogonal operators, but the precise geometric viewpoint for a unitary or an orthogonal operators is that these operators are length preserving operators. That's exactly the motivation behind defining these operators, unitary or orthogonal. So these are basically length preserving operators. For example, if you choose a rotational operator, which you can just give by the matrix cos theta sin theta minus sin theta cos theta, or you can talk about a reflection operator. Reflection operator, you can give a definition. So let me just start arbitrarily with a definition. Let L be a one dimensional subspace. So it's basically, you can think of it as a line. So it's a one dimensional subspace of R2. What more can I say? Let me choose an operator. Let T belong to the collection of all linear operators on R2 such that T of x is equals to x if x is in L, and T of x is equals to minus x if x is in the orthogonal complement of L. Okay, or you can think of it as if you choose a line perpendicular to L, or if you choose all the set of lines which are perpendicular to L, typically you will eventually get sort of a plane, right? If you choose a line, if you simply choose a line L, so let me just precisely give you like this. So suppose this is your R2 and you fix some line on it. Suppose you fix this line, let's say you fix this line, suppose this is L. Then there are infinite number of lines which are perpendicular to L. So you have lines like this, right? And there are infinitely many of them. So what I am trying to say here is that if I choose any point which is on L, so if I choose a point here, then T will map this point x to itself, so there will be no change in its position. But if I choose a point from here, then I'll map it to the negative of it. That's what I exactly mean. So I'll just reflect it about this line L. Clear? I'll just reflect this about reflect the point about the line L. So this is called a reflection. So T is called a reflection of R2 about L. And since we are only reflecting a line, so it's obvious that this operator is still length preserving, which you can easily observe by its definition as well, right? Moreover, this is pretty observable that if I choose a vector v1 from L and I choose a vector v2 from its orthogonal complement, then what more can I say from here is that yeah, so I have T of v1 to be minus v1. Sorry, I have T of v1 to be just v1. So the eigenvalue which to which v1 corresponds to as an eigenvector is just 1, and furthermore I can write T of v2 as minus v2. So I can also, so this basically speaks of the fact that v2 corresponds to the eigenvalue minus 1. Moreover, they come from moreover v1 v2 are orthogonal, right? So suppose I choose v1 and v2 such that their norms are 1, their norms are 1, then I'll eventually reach an orthonormal basis. I'll eventually reach an orthonormal basis. So I start with a unitary operator and I eventually reach an orthonormal basis using the elements which gets mapped or which are very specific under the image of T as a linear operator. So this actually gives us an important proposition. You might say it as a proposition, or you might also say it to be a corollary of the previous set of equivalence statements. Whatever, let me just independently write it as a proposition. So let T be a linear operator on V, where V is a finite dimensional inner product space over R. So we are specifically talking over R. Then V has an orthonormal basis of eigenvectors. Then V has an orthonormal basis of eigenvectors of T, and precisely of absolute value 1 if and only if eigenvectors of T corresponding to eigenvalues of absolute value 1 if and only if T is self adjoint and orthogonal. So in the above example, we were completely confined to the real vector space. Hence I have been constantly using the term unitary, but we can obviously talk about it being orthogonal since we are talking inside a real vector space. And you can easily observe out this theorem in this example, that the eigenvalues are precisely 1 and minus 1. So both of them are having their absolute values to be 1. Moreover, this is very easily observable, and we had also seen this as an example of a self adjoint operator, right? There is nothing too difficult in it. If you just consider the matrix of T with respect to, let's say, the standard ordered basis of R2, then you will see that it basically will give you a symmetric matrix, a real symmetric matrix. It will get out from T. So you can easily observe that. For example, so T of, so this will give you an orthonormal basis, right? You can just try and map it out from the matrix of T from this basis as well, right? So you will get 1 0 and then you will get 0 minus 1. That's exactly what you will get, right? So it will eventually follow out from here as well. Whatever, let's give a proof of this, then it will be more precise. The proof. Now previously we have already seen the fact that if we are talking about a self adjoint operator over obviously a finite dimensional linear product space over R, then it will precisely have an orthonormal basis of eigenvectors, right? So first part is pretty obvious, that if T is self adjoint, then T has an orthonormal basis, of eigenvectors. Then V has an orthonormal basis of eigenvectors of T. And just so we need to show that the corresponding eigenvalues are having absolute value 1. So to show it, so suppose I consider this orthonormal basis to be, let's say V1 V2 till Vn, and let lambda I be the corresponding eigenvalue of Vi. Okay. Then observe that I can write, so I need to show that the absolute value of lambda I is 1. So I must take mod of lambda I times the norm of Vi, and the reason is that I can map it, I can equally write it as mod of norm of lambda I times Vi, but then this is nothing but norm of Tvi Okay. Now observe that T is orthogonal as well, so it's length preserving. So this should be equal to norm of Vi, which means that mod of lambda I must be equals to 1, right? Because we are getting a orthonormal basis, right? So norm of each of these Vi's are 1, right? And this happens for all i's equals to 1 to n. So this is pretty easy. And the converse part is also pretty easy as well. That is, if we have an orthonormal basis of eigenvectors of T, then this was basically a characterization of a self-adjoint operator, that T is self-adjoint if and only if the vector space has a orthonormal basis orthonormal basis of eigenvectors of T, right? So suppose V has an eigenbasis, V has an orthonormal eigenbasis, then T is self-adjoint. But what more we are given is that the corresponding eigenvalues are having absolute value 1, and what more we need to show is that T is orthogonal. But that's quite easy to show, because observe that if I choose out any element from the orthonormal eigenbasis, suppose Vi is an element, of the orthonormal eigenbasis, okay, then what is T star of Vi? So it should be precisely T star of Vi, right? But we know that in case of a complex normal operator or a real self-adjoint operator, if Vi is an eigenvector corresponding to an eigenvalue lambda I, then Vi is an eigenvector of T star as well corresponding to the eigenvalue lambda I bar. So this will basically give you T of lambda I bar Vi, but lambda I bar is a scalar value, so it will eventually come out, and then you will be left with T of Vi, but T of Vi will be lambda I times Vi. So this is nothing but lambda I bar lambda I Vi, but lambda I bar will give you mod of lambda I squared Vi, but we are given that the corresponding eigenvalues are having absolute value 1, so this is just Vi, right? Therefore T star equals the identity operator on the basis elements. And since we are talking about linear transformations and we have an equality in terms of the basis elements, so we will also have an equality in terms of any linear combination of the basis elements. In other words, we will have T star of V to be equal to V for all V in capital V, which would eventually mean T star is equals to I, which is equivalent to saying that T is orthogonal. Okay. So this is another fine characterization of orthogonal operators, or as I mean to say orthogonal and self-adjoint operators, that in that case we will have an orthonormal basis of eigenvectors corresponding to eigenvalues of absolute value less than 1. Now obviously there is nothing too specific about it being an orthogonal operator, since we are working over a real inner product space. So if I restrict, or rather if I generalize this to a complex vector space, then I can eventually talk the same about unitary operators, right? So I can just similarly I can say that let T is real inner operator on V, where V is a finite dimensional inner product space over C. Then V has an orthonormal basis of eigenvectors of T corresponding to eigenvalues of absolute value 1 if and only if T is unitary, and this is sufficient. Okay, clear? Okay. Now some immediate observations about these unitary and orthogonal operators. See, if I prove anything about unitary operators, then I will eventually get I will eventually get the same observation for a unitary operator as well, right? So let me just change the page. Yeah. Okay, so yeah, yeah. So observe that, suppose A is a square matrix. Suppose A is a square matrix. Let's say over C. Then we can define A. Then A is said to be unitary if, what should be the immediate observation? If A star is same as A star A is equals to I, and it will be eventually said to be orthogonal over R if A transpose is same as A transpose A is equals to I, right. This is immediately coming from the equivalence statements that T star is equals to I, and yeah, so we are not very much interested in defining a transpose of a linear operator. The adjoint is a well defined concept though. Whatever, I guess this part is clear. The thing which I actually want to observe is that suppose A is unitary, we are talking about matrices. Suppose A is unitary, then observe that A star is equals to I. So this is equivalent to speaking that the ijth element of A star corresponds to the ijth element of the identity matrix, right. So A star, the ijth element of A star equals the ijth element of I, but this eventually means that, so what should be the ijth element of A star? So if I expand the matrix operation, so this will similarly come to be this, say k is equals to 1 to n. So we are talking about an n cross n matrix, let's say. So k is equals to 1 to n A I k, but instead of A star kj, I can just write it as A j k bar, right. A star kj is actually the transpose of the conjugate of the matrix A, right, or the element ajk. So I can just remove the transpose and I'll get the element ajk, and just keeping the conjugate there, I'll get my answer. So this is, I guess this part is pretty evident. So this should be equals to delta ij, right. This should be equals to delta ij. But observe that this is nothing but a matrix norm. This is nothing but, or if you don't know, you can just define it equivalently here. This is just a matrix norm. So what is, so this is, see, this is exactly how we define norms on n tuple spaces. Okay, we are just multiplying elements from each row component wise. For example, if I have two rows, let's say 203 and 302, then I am just multiplying 2 times 3. What I am doing here is that, so 2 times 3 bar specifically, so I am multiplying 2 times 3 bar plus 0 times 0 bar plus 3 times 2 bar, and you can obviously relate it to the standard norm defined on n tuple spaces, right, on Cn, let's say. So this is simply the matrix norm. So what we are eventually getting is that the matrix norm of the elements correspond to the Kronecker delta, or in other words, this exactly means that the rows are orthogonal. The rows are orthogonal, or in fact we can say something more, it's orthonormal, because we are eventually equaling a Kronecker delta. So it's just not orthogonal, it's orthonormal, right. So the rows are orthonormal, and there are exactly n rows, and we are working obviously inside an n dimensional space because we are working with an n cross n matrix. So the rows eventually form rows. So since we are having orthonormal rows, so we will obviously, so trivially we are having orthogonal rows, so hence we are working with linearly independent rows. So we are eventually getting a orthonormal basis. So the rows are orthonormal basis for Fn. Clear? And similarly we can say the same for columns as well. Just you just require a column expansion, then you are done. So you can say the same for columns as well. The columns of an unitary matrix will form a orthonormal basis for Fn. Okay. Clear? Now in terms of a linear operator, you can equivalently say that a linear operator can be said to be unitary if the matrix of the linear operator corresponding to, say, let's the standard ordered basis is unitary. Yeah, the standard ordered basis will suffice because that's indeed an orthonormal basis. Whatever, let's let us check a very important observation now. Observation. See, suppose I choose a complex normal matrix. Let A be a complex normal matrix, or equivalently say a real symmetric matrix. So if I talk about a complex normal matrix or a real symmetric matrix, then typically I can say that A is diagonalizable. A is diagonalizable, right? Because we have already seen that if we are talking about a linear operator about a finite dimensional complex space where the linear operator is normal, then the space has a orthonormal basis corresponding to eigenvectors, sorry, with eigenvectors of that operator. That eventually means that if I talk about a matrix associated with that linear operator, it will eventually mean that that matrix is diagonalizable. And so we are defining the exactly same thing in terms of simply matrices, independently in terms of matrices. So we can say that A is diagonalizable since, so we can just induce it in reverse way, that we can talk about the same thing in terms of Fn, right? Because if I start with a matrix and I want to construct an operator out of that matrix, I will eventually land into the space Fn. So A is diagonalizable as Fn has an orthonormal basis of eigenvectors as eigenvectors of A, right? So suppose A is diagonalizable, so let this diagonal matrix be D. So then we have that A is similar to D, right? A is similar to D, or which is equivalent to saying that A can be written as Q inverse DQ with some invertible matrix Q, right? There is nothing too complicated in this case, or am I writing it in some reverse order? Sorry, this should be Q, or let me write it in this way. Yeah, because AQ equals QD, right? Yeah, AQ equals QD. So this should be written as D is equals to Q inverse AD, AQ, right? Clear. But the question is that now Q is an unitary matrix. Q is unitary. Why is Q unitary? Because recall this fact. So why is Q unitary? Recall let A be a n cross n matrix over a field, and let gamma be an ordered basis, let gamma be an ordered basis of Fn. Then the matrix of the linear operator induced by A in terms of gamma, this is simply Q inverse AQ, right? So this is just this change of basis method in terms of matrix. So this is something we know, but how can we construct Q? So where Q is n cross n matrix, this is why I wanted to recall this theorem. So Q is n cross n matrix whose jth column is the jth vector of gamma. That's exactly what I wanted to say. So if I go back to what I was trying to speak here, so this Q, when I am talking about this Q, so this Q eventually it comprises this Q comprises of each of its columns as the vectors of the eigenbasis, right? As the vectors of the eigenbasis, and that very basis is an orthonormal basis, right? therefore the columns of Q are orthonormal. What we are getting is that columns of Q are orthonormal, but if columns of Q are orthonormal, then Q is eventually unitary matrix. Now, since we have an orthonormal basis, columns of Q are eventually orthonormal. But we have just seen that if columns of a matrix are coming out to be orthonormal, then the matrix is specifically unitary, which means Q is unitary, or in other words, the inverse of Q is equivalently the adjoint of Q, right? Therefore, I can write D as Q star A Q, right? Clear? Okay. Therefore, this leads us to a very important concept which we call unitary equivalence. This leads us to what we call unitary equivalence. So, definition: two matrices, let A and B be complex n cross n matrices, then A is said to be unitary equivalent, then A is said to be unitary equivalent to B, or you can eventually say that A and V are unitary equivalent if and only if A can be written as P star B P. Yeah, this will do. And eventually you can similarly talk about an orthogonal equivalence. In case of an orthogonal equivalence, you will just get Q star to be the transpose of Q, nothing else. Okay. Similarly, you can talk about an orthogonal equivalence. Similarly, you can talk about orthogonal equivalence. Clear? Okay. So, clear? Yeah, okay. Now, so whatever observation we were talking about before this definition, that can be actually summarized into this theorem, that let A be a complex n cross n matrix, then A is normal. Then we had a one-sided implication in the observation, but we can actually make it an equivalent statement. Then A is normal if and only if A is unitary equivalent to a diagonal matrix, and this theorem to a diagonal matrix, and this theorem is actually motivated by the fact that when we are talking about about a normal matrix or a normal operator, you can say, then precisely I can equivalently I am equivalently talking about the space in which we are talking to have an orthonormal basis of eigenvectors, right? But we have already shown that if A is normal, then A is unitary equivalent to a diagonal matrix. So we are just left to show the converse part, that suppose A is unitary equivalent to a diagonal matrix. So let A be written as P star dP, where D is diagonal, obviously, but D is diagonal. Then this implies A star is equal to P star dP times P star dP whole star, but this is nothing but P star dP times P star D star P, but D star P is nothing but, actually it will be giving you just the conjugate of each of the elements in D, whatever. So it eventually becomes so P is unitary, right? So it will give you P D star P, right? It will give you P star D star P. Similarly, if you do the same thing for A star A, you will eventually rate P star D star DP. Okay, but then since D is diagonal, what I was just saying is that since D is diagonal, so there is no concept of a transpose, right? you will just get the conjugate of the elements in the diagonal, but so it's still a diagonal matrix, and diagonal matrices commute, right? So you will eventually get P star D star P, which is simply A star. Therefore A is normal. Therefore A is normal, right? There's nothing too complicated here. And equivalently you can also state this theorem in terms of a real matrix, that is, let A be a n cross n real matrix, then A is symmetric if and only if it's orthogonal equivalent to a real diagonal matrix, okay, to a real diagonal matrix. Clear? Got it? Okay. Now how can we eventually find this vectors Q? Okay, so let me start with that. See, how should I actually get this? See, if I start with the matrix, which is an example, let's say 4 2 2 2 4 2 2 2 4, okay, then what should be the eigenvalues of A? Okay. What should be the eigenvalues of A? See, I can actually see the row sums are actually 4 2 6 to 8, so 8 must be an eigenvalue. All the row sums and columns are eventually giving you the value 8, so 8 is obviously an eigenvalue. The trace is 12, right? The trace is 12. Yeah, I guess eventually we will get 2 2 and 8 to be the eigenvalues, okay. What should be the corresponding eigenbases, right? So I have, say, A x is equals to 2x, right? Let me just calculate it out once. Wait. So yeah, so in this case I'll get, yeah, okay, okay. So therefore the eigenspace corresponding to 2 will come out to be let's say -110 and -101. So this is a standard example, okay, while that for 8 will be 1 1 1. Okay, let me just first check whether we are getting a diagonal matrix or not. So what is so we have 4 2 2 2 4 2 2 2 and 4. So we want to multiply it with -1 1 0 -1 0 1 and 1 1 and 1. So what should I get? So 4 times -1 plus 2 I'm getting here, so I'm getting here -2. So here I have 4 times -1, so -4 plus 2, I'm getting here -2, and I'm getting here 4 times 1 plus 2 plus 2, so 4 and 4 8, right? Here I'm getting -2 plus 4, so 2 -2 and plus 2, so 0. I'm getting 2 4, so I'm getting 8 here again, and -2 and plus 2, so I'll get 0, -2 and plus 4, so I'll get 2, and I'm getting here 8 again, right? So what should be -1 1 0 -1 0 1 1 1 1 times what should be diagonal matrix? So it should be 2 2 and 8, what should be this? Let me just calculate it out. So it's minus 1 times 2 plus minus 1 times 0 plus 1 times 0, so minus 2 here. I have minus 1 times 0 plus minus 1 times 2 plus 1 times 0, so I have minus 2 here. I have minus 1 times 0, I have 8 here. 1 times 2, 0 times 0, 1 times 0, so I have 2 here. 1 times 0, 0 times 2, 1 times 0, so I have 0 here. 1 times 8, sorry, 1 times 0, 0 times 0, 1 times 8, 8 here. 0, 0, 0, 0, 2, 0, so I have 2 here, and I am having 8 here. So these are eventually same. Yeah, correct, right? So this will comprise as the matrix such that A is written as Q D Q inverse. Okay, but we need a matrix which is unitary, which establishes the unitary equivalence. So for that, what I can do exactly is that I can actually orthonormalize the eigenspace with respect to 2 and with respect to 8. Now with respect to 8, we nothing to have do much, we just need to orthonormalize it, or rather we just need to normalize it. We don't have to do anything in terms of orthogonalization because we just have a single vector. Okay, so applying the Gram-Schmidt orthogonalization process to the space minus 1 1 0 and minus 1 0 1, we get, so it is very easy to observe that we get minus 1 1 0 and we get, so I should get here minus 1 over 2 1 1 and minus 2. Okay, done. And so we just have to take an union of this with the vector 1 1 1. So this will form you the orthogonal basis in at least in this case, but we just need to normalize it. So we will get the vector. So here I'll get 1 upon root 2, right? 1 upon root 2 minus 1 1 0. I'll get here, so 1 and 1 and 4 to 6, right? So I should get here 1 1 minus 2 1 over root 6, and what more should I get? This is 1 over root 3 1 1 and 1, right? So eventually where should I land? So I should get this matrix, right? So I just need to arrange them in columns. So I should get here minus 1 over root 2, 1 over root 2 and 0. I should get 1 over root 6, 1 over root 6 and minus 2 over root 6, and I have here 1 over root 3, 1 over root 3 and 1 over root 3, right? This is what I should get. Clear? Okay. Yeah. So this will do. So this should be the orthonormal basis we should talk about, which will eventually give you this unitary matrix. So this will serve as, let's say, P, and the diagonal matrix is obvious. So it's 2 2 8. Okay. There's nothing too complicated to talk about now in this case. But let me end this lecture by just giving the analogous Schur's theorem. Schur's analog of matrices. This part of the lectures on linear algebra started with a Schur's theorem on linear operators, but we are ending this part. We are not actually ending. There will be one more part where I will be talking about rigid motions, and I will be talking about orthogonal projections. But yeah, this can be thought of some sort of a summary. So Schur's analog of matrices theorem. It is very simple. So let A be an M cross N matrix from a field F whose characteristic ball splits over F. Then number 1, if F is the complex field, then A is unitary equivalent to a upper triangular matrix, to an upper triangular matrix, and if the field is a real field, then A is orthogonal equivalent to a real upper triangular matrix, to a real upper triangular matrix, right. So, talking about similarity can be brought down to talking about equivalence in terms of unitary matrices and orthogonal matrices. The next lecture will be a short lecture on the concept of rigid motions. So, rigid motions is a special type of operators which are distance preserving, which are sort of distance preserving. Like we have talked about many sort of preservations in terms of these operators. So, now we want to talk about operators which are some sort of a distance preserving operators. Okay. And one of the prime examples of such an operator is what a translational operator. What a translational operator, that is, it just translates, translation operator. So, it just, suppose is a vector, it just translates the vector to some other place, but the points on the vector will still have the same distance as it was previously. Okay. And a basic definition is actually very simple. So, let me just give the definition and end this lecture. Definition: let V be a real inner product space. These sort of things we will be eventually talking about a real inner product space, because these are having a important geometric viewpoint. So, let V be a real inner product space, then a function on V is called a rigid motion, is called a rigid motion if it's distance preserving. So, if the norm of fx minus fy is same as the norm of x minus y, and this happens for all x, y in P. Okay. And what are the most important examples? These examples which we have already seen, the examples I can clearly talk about are, firstly, the orthogonal operators. The orthogonal operators, because these, first of all, these are linear operators, because these are linear operators. So, the norm of fx minus fy, if this is a linear operator, this will eventually become f of x minus y, but orthogonal operators are distance preserving operators. So, it will eventually be the norm of x minus y. And next we have what we call the translational operators. The translational operators. So, translational operators are basically, so let me just precisely say it here, that G from V to V, where V is again a real inner product space, is called a translation, is called a translation if there exists a vector V naught in V such that I just map x by translating it by V naught, and this happens for all x in V. Okay. So, in this case we say G to be a translation by the vector V naught, and since there is no scaling factor here in this case specifically, so the distance between 2 points will still get preserved after even mapping the vector to some other place, right. So, this will again come out to be a rigid motion. The important fact about this portion is that, and this is sort of a characterization, that if I talk about a function over a real inner product space which is a rigid motion, then actually I can talk about that function to be the composition of an orthogonal operator and a translation on V. So, rigid motions, so specifically, see, since orthogonal operators are distance preserving and translational operators are distance preserving, so the composition will eventually be distance preserving. But if I start with a rigid motion, I can actually write it as an orthogonal, so an orthogonal implication composed with a translational implication. Okay, but so this T is orthogonal operator, which will be uniquely determined, and this G is a translational operator. Again, this will also be uniquely determined. Okay. So if I talk about a distance preserving function on a real linear product space, then actually equivalently I am talking about doing an orthogonal, so doing some so applying an orthogonal operator on it and then just translating it by some vector. Okay. Yeah. So that's enough for today. In the next lecture we will prove this theorem, and then we will be moving on to the concepts of orthogonal projections. So meet you guys in the next lecture.